So if you miscalculate the length of a steel beam on an offshore oil rig, you might lose, a few $100s.
Right, which is annoying but manageable.
Exactly. But if you fundamentally misunderstand the legal rule book for how to paint that exact same beam, you could honestly bankrupt your entire company.
You really could. It's that serious.
Welcome to our latest deep dive. Today, we're opening up the hidden architecture behind a process that honestly seems completely mundane on the surface. We're talking about industrial painting.
Yeah, and it's actually a highly regulated, just mathematically ruthless matrix of risk allocation and chemistry, too.
Right. And our source material today is intense. We're looking at excerpts from the FEIC Red Book construction contract, which, for those who don't know, is basically the global gold standard for international mega projects.
Absolutely. Specifically, we're digging into the unit rate schedules and the pricing preambles.
And these documents, they completely shatter any illusion that painting a chemical plant is about making it look pretty, right?
Oh, yeah. A coat of paint in this environment is a primary structural defense system, and the rules governing how you price it, how you measure it, and apply it are just remarkably rigid.
So let's just start with the sheer geometry of the job, because before a contractor can even price a surface, they have to measure it.
They have to know what they're dealing with.
And the FIDIC preambles prove that measuring an industrial facility is not, just a simple length times width calculation.
No, not at all. The rules actually force contractors to absorb specific operational inefficiencies.
Like what? Give us an example.
So, for instance, the preambles dictate that general surfaces are measured in square meters. But, and this is key, contractors make absolutely no deductions for voids.
Voids like holes or gaps in the steel.
Exactly. If the void is less than 1.0 square meter in area, you do not deduct it from your total measurement.
Wait, really? So you get paid for painting a hole?
Basically, yeah. And the underlying logic there is purely about labor economics.
Meaning what, exactly?
Well, think about the administrative cost. Having a surveyor walk around with a clipboard, carefully measuring a half square meter access hatch, and then deducting that tiny void from the overall structural area.
Oh, I see. That whole process of measuring the hole just costs way more than the paint you'd save anyway?
Exactly. The contract standardizes that inefficiency. You just treat the void as if it's solid steel, you get paid for it, and the math moves a lot faster.
That is wild. And then you look at how they handle pipework, and the spatial logic just completely shifts.
Well, pipework is a whole different beast.
Yeah, the preambles say pipes are measured in linear meters along the center line, and you measure straight through inline fittings like bends, elbows, and T's. But, and this is the part that got me, you strictly exclude inline equipment like valves.
Yep, valves are explicitly left out of that linear measurement.
Which, if I'm looking at this just from a geometric standpoint, an elbow joint is really just a bent cylinder. The surface area math is pretty constant compared to a straight pipe. But a valve is a topographical nightmare.
It's a complete nightmare. I mean, a valve, especially a large motor-operated valve or a control valve, it introduces massive mechanical complexity.
Right, because of all the moving parts.
Yeah, you've got exposed stems, moving actuators, flanges, really delicate seals. A contractor applying heavy industrial epoxy can't just spray over a valve the way they would a straight run of carbon steel.
Oh, because if you spray it, you just glue the whole thing shut.
Exactly. If that coating fuses the valve stem, you've completely disabled a critical control mechanism for the entire pipeline. So the preamble forces a completely different pricing structure there.
So how do they price it then?
Valves are enumerated. You literally count them one by one, categorize them by diameter and type, and then you price that meticulous brush-applied labor completely separately.
Okay, that makes sense. But that brings us to the rule that seems to carry, the most hidden financial risk for a contractor. Corrugated or profiled steelwork?
Oh, yeah. This is a big one.
The preambles literally state this material is measured strictly by its net plan or elevation area, meaning there is absolutely no extra allowance for the added surface area created by the peaks and valleys in the metal.
Not at all.
So wait, if I'm a contractor, it's like I'm agreeing to paint a flat piece of paper for $10. But when I show up on site, that paper is folded into a complex origami crane.
That's a great way to put it.
And I'm only getting paid for the 2D footprint of that crane. I just have to eat the cost of painting all those extra hidden folds.
That is exactly what happens. The contractor is expected to understand the geometric reality of corrugated steel long before they even submit a bid.
Wow.
Yeah, so if a specific profile of corrugated steel has a surface area that's, say, 1.4 times larger than its flat footprint,
The contractor just has to know that.
yeah, they have to calculate that corrugation factor themselves, and then they bake the extra labor and material costs into their initial unit rate.
Because the client is literally just buying the coverage area on their blueprint.
Exactly right. The burden of calculating the physical reality of the metal falls 100% on the contractor.
And that burden even extends to how they categorize different objects, right? Like general structural supports are measured by weight in kilograms, but completed ladders and handrails are measured in linear meters.
Yes, the physical metric literally changes based on what's the most efficient way to capture the labor cost.
So like weighing a bucket of hundreds of complex steel pipe brackets is a much more reliable proxy for the labor required to paint them, right? Because calculating the surface area of every individual tiny bracket would take weeks.
Exactly. It's all about finding the most practical proxy for the work. And all of these measurements eventually feed into what the contract calls a composite rate.
The composite rate. Okay, let's talk about that. Because when an employer pays this rate for supply, prepare surface, and apply coating, the actual spraying of the liquid paint is basically the cheapest, fastest fraction of the entire job.
It's the tip of the iceberg. The rate is actually funding this massive, incredibly strict scientific ecosystem of preparation and environmental control.
Right, let's unpack that prep phase. Because the preambles mandate that the unit rate covers solvent washing to strip away machine oils, and then it's followed by abrasive blasting to take the steel all the way down to its raw state.
Yep, all the way to bare metal.
I'm assuming this isn't just about making the metal look clean. There has to be a mechanical necessity for blasting the steel before you put epoxy on it.
Oh, there is. Heavy industrial coatings, they just do not stick to smooth surfaces.
They just slide right off.
Basically. So abrasive blasting fires grit at the steel at extreme velocities to create what we call an anchor profile.
An anchor profile?
Yeah, it microscopically shreds the surface of the steel. It creates these tiny jagged peaks and valleys.
So the pellet has something to hold on to?
Exactly. When the epoxy is applied, it flows into those valleys and cures.
Yeah.
And that creates a really profound mechanical lock with the steel substrate.
And if you don't do that, like if you leave a little oil on the surface or you don't get a good anchor profile,
then the epoxy will just cure into a hard shell that eventually peels off in massive sheets. It's a complete failure.
good grief. And the preamble actually goes even deeper into risk mitigation during this prep phase. It specifically mandates the masking of welds.
This is a really crucial detail.
Right. The contractor has to carefully protect all the weld seams, leaving them totally uncoated until after the pipeline has undergone hydro testing.
Right, because hydro testing is where they check the structural integrity of the pipe. They fill the completed pipeline with water and pressurize it to levels far beyond its normal operating capacity.
So they're stress testing the welds, but why can't the welds be painted first?
Because if a contractor applied a really thick, high-build epoxy coating over a weld before that pressure test, the coating is actually strong enough to temporarily plug a micro crack in the weld.
Wait, really? The paint is that strong?
It is. So the pipe would pass the pressure test, it's completely fine, and then go into a live operation carrying, hazardous chemicals.
Oh, no.
And eventually, the crack would propagate right through the paint, causing a catastrophic failure.
That is terrifying. So the contractor is essentially being paid to not paint, wait for the mechanical engineers to stress test the system, and then they have to mobilize their crews a whole second time just to unmask, prep, and coat those specific weld lines.
Yep. It's a massive logistical dance.
Yeah.
And honestly, this entire dance is governed by what might be the most unpredictable variable in the whole contract.
Which is what? The weather.
Exactly. Ambient conditions. The composite rate explicitly includes testing to ensure compliance with temperature, relative humidity, and the dew point.
Does this mean the painting contractor is legally and financially on the hook if the humidity or temperature is wrong on painting day? Like they have to act as local meteorologists.
They absolutely do. And the dew point is the really critical metric here.
Okay, break that down for us. Why the dew point?
Because paint curing is a chemical reaction that is highly, highly sensitive to moisture. If the temperature of the raw, freshly blasted steel is too close to the dew point of the surrounding air, invisible condensation forms on the metal.
So the steel looks dry, but it's actually wet.
Exactly. So the contractor isn't just applying paint to steel. They're unknowingly applying paint to a microscopic layer of water.
And I'm guessing the epoxy doesn't like water.
Not at all. The epoxy will happily bond to the water instead of the steel anchor profile we just talked about.
Oh, wow.
And the moment that moisture evaporates or the steel expands under the hot sun, the coating completely fails.
And because the FIDIC contract legally embeds that compliance with ambient conditions directly into the unit rate.
The contractor absorbs the entire cost. If they rush a job on a morning with high humidity and the coating fails an adhesion test 2 weeks later, they pay for it all. Erecting the scaffolding, reblasting the steel down to bare metal, reapplying everything, all out of pocket.
That's insane. You're managing hundreds of workers, coordinating with pipe layers, and your entire profit margin is tethered to a literal hygrometer.
It really is.
So, okay, assuming the weather actually holds and the surface is pricked perfectly, the contractor then has to navigate the WBS codes.
Right. A work breakdown structure.
Yeah, this is a 7-level alphanumeric matrix that categorizes every single physical object on the site. And level 4 codes specifically dictate the chemical approach, right? Like you have SP0 for carbon steel, SP1 for stainless steel, SP2 for galvanized carbon steel.
Yeah, the WBS code is basically a translation layer between the engineering reality on the ground and the financial ledger.
Why do they need to separate them out so strictly, though? Paint is paint, right?
Well, you cannot treat carbon steel and stainless steel with the same abrasive blasting protocol.
Oh, really? Why not?
If you blast stainless steel with the same aluminum oxide or steel grit that you just used on a carbon steel pipe, you will actually embed free iron particles into the stainless surface.
Wait, so you're basically shooting rust into the rust-resistant steel?
Exactly. You will essentially infect a rust-resistant alloy with rust. It completely ruins the material.
Oh, man. It's like, okay, it's similar to the strict protocols in a high-end commercial kitchen, right? Like, if you use a metal spatula on a cast iron skillet, it's totally fine.
Right.
But if you absentmindedly use that exact same metal spatula on a Teflon-coated pan, you scar the surface and compromise the entire nonstick function.
That is a perfect analogy. The WBS codes ensure you never bring the wrong tool or chemical to the underlying substrate.
And the granularity of these codes is just staggering. I was looking at level 7, which categorizes pipe diameters. The schedule literally lists WBS codes starting at a tiny 1/4-inch pipe and goes line by line all the way up to massive 44-inch pipelines.
And there's a very good reason for that. The labor mechanics shift drastically across those different diameters.
How so? Like big pipe equals more paint.
It's more about how you apply it. A 44-inch pipe presents a massive, relatively flat curve. So a painter can efficiently use industrial spray equipment to coat large sections really rapidly. Very little paint is lost to overspray.
Right, because it's a huge target.
Exactly.
Yeah.
But a 1/4-inch pipe, that's essentially just a thin line hanging in the air.
So if you spray it.
You waste a tremendous amount of incredibly expensive coating directly into the wind. So for those, the contractor often has to rely on slower, meticulous brush or roller applications.
Oh, I see. So the WBS code isolates that specific inefficiency so the contractor can price the manual labor accurately.
Exactly.
That structural complexity, though, it really peaks when you look at the codes for special pipe supports. The preambles have specific designations for clamp types, spring hanger variable types, and the one that really caught my attention, shoe PTFE types.
Ah, yes.
PTFE is essentially Teflon, so we have heavy industrial pipes literally resting on Teflon shoes. Why?
Because industrial pipelines transport materials at extreme temperatures. We're talking superheated steam or cryogenic liquids.
Okay, so really hot or really cold?
Right. And steel pipes expand and contract significantly as the temperature fluctuates. If you were to bolt a mile-long pipeline rigidly to its concrete supports, the thermal expansion would literally tear the steel structures right out of the concrete.
Wow, just from the metal expanding?
Yeah, the forces are massive. So instead, the pipe rests on a Teflon shoe. This allows it to slide back and forth with very low friction as it grows and shrinks.
That is brilliant engineering, but painting around that has to be awful.
It's incredibly difficult. Painting around a dynamic load-bearing sliding mechanism requires immense precision. Because if you get even a little bit of industrial epoxy on that Teflon sliding surface...
You've just introduced friction.
Exactly. Which defeats the entire engineering purpose of the support in the first place.
Unbelievable. So every single WBS code represents a unique physical constraint. But after navigating the measurement quirks, the surface prep chemistry, all those alphanumeric codes, we finally reach the last layer of the preamble, the actual function of the coating itself.
Right, because in these industrial environments, the top coat isn't just a physical barrier. It serves a critical informational role.
Yeah, the preambles mandate the inclusion of complex color coding systems, identification banding, flow arrows, product legends. The paint is literally the primary user interface for the facility.
It really is.
Yeah.
Think about a processing plant containing thousands of identical-looking steel pipes. Visual communication in that space is a matter of life and death.
Absolutely.
A worker, or say an emergency responder, they need to know instantly from 50 feet away whether a specific pipe is carrying pressurized firewater, highly corrosive sulfuric acid, or lethal hydrogen sulfide gas.
The pipes might be heavily armored, but they're basically wearing name tags and giving you directional instructions so you don't get lost, or worse, in an emergency.
Exactly. And the contract explicitly ties this color coding to statutory safety requirements.
Right, like the rates for coating platforms, stairways, and handrails. They expressly include specific color coding for emergency escape routes. The literal paint on the handrail dictates the path you have to take when the alarms sound.
It's your lifeline. And to really understand the extremes of this protective infrastructure, we have to look at two highly specific WBS codes at the far ends of the spectrum, SP7 and SP8.
Let's start with SP7, galvanizing. The source text makes it clear this isn't a liquid paint at all, is it?
No, not at all. It's a metallurgical process. It's where the steel is fundamentally bonded with a layer of zinc, and the zinc acts as what we call a sacrificial anode.
Okay, explain the mechanism behind a sacrificial anode. How exactly does bonding zinc to steel prevent the steel from rusting?
It relies entirely on electrochemical principles. Zinc is simply more electrically active, or what we call less noble, than carbon steel.
Okay, so when they're bonded together...
Right, when the two metals are bonded and they're exposed to an electrolyte like, say, salt water or heavy industrial humidity, a galvanic cell is formed.
Kind of like a battery.
Very much like a battery. And in this cell, the zinc willingly gives up its electrons to the steel. The zinc is what corrodes and degrades over time. It literally sacrifices its own atomic structure to keep the carbon steel beneath it completely pristine.
That is just a fascinating passive defense system. It's taking a bullet for the steel.
Essentially, yes.
And then we have SP8, which is fireproofing. The preambles detail that fireproofing rates include fixing, meshing, mastic, and sealant, all measured in square meters of the structural steelwork.
This implies we aren't just rolling on a flame-retardant paint. We are building a serious physical barrier.
Oh, absolutely. Because structural carbon steel, it actually loses a massive percentage of its load-bearing capacity when it reaches roughly 500 degrees Celsius.
Which in a hydrocarbon fire, I assume happens pretty fast.
In minutes.
Yeah.
Temperatures hit that threshold incredibly fast. So industrial fireproofing, it actually involves welding metal pins to the beam, then wrapping the steel in wire mesh, and troweling on this incredibly thick cementitious mastic.
Wow, so it's practically concrete. Yeah, it's thick. And this mastic contains chemical hydrates. So when it's exposed to extreme heat, it undergoes an endothermic reaction.
Meaning it absorbs heat.
Right. It releases water vapor that literally absorbs the thermal energy from the fire.
That's incredible. So the sole purpose of that SP8 coating is to just buy the structural steel an hour or two of time before it hits its critical failure temperature.
Exactly.
It just buys the steel enough time so the structure doesn't collapse while the workers use those color-coded handrails to evacuate.
Precisely. It is a highly calibrated, mathematically priced delay mechanism.
We started this deep dive looking at a simple coat of paint. But digging into these FIDIC Red Book preambles reveals this massive, invisible, high-stakes infrastructure that's required to apply that coating in an industrial setting.
It's so much more than just the liquid in a bucket.
It really is. You know, you are looking at a surface that was meticulously measured by its net plan area, right? Blasted to a microscopic anchor profile, painstakingly tested against the ambient dew point, tracked by an alphanumeric WBS code, and then engineered to sacrifice its own electrons to maintain the structural integrity of a multi-billion-dollar facility.
It completely reframes how you look at the built environment, doesn't it?
Totally.
I mean, if a single millimeter of industrial coating requires this much legal, mathematical, and thermodynamic infrastructure just to exist,
Yeah.
how much invisible, unwritten data is holding together the bridges, the tunnels, and the buildings you interact with every single day?
That is wild to think about. Next time you walk past a painted steel column, remember the sheer volume of engineering and contract law keeping that surface intact. Thanks for joining us on this deep dive. We'll catch you next time.
If you're interested in the templates, please visit our shop. The link is in the description.
Thanks for watching. Please subscribe and see next time.